Okay, let's just quickly go over the solutions. So for problem 1, the reason why the saturation current for a short channel MOSFET only depends linearly on VGS minus VT, which often we call that the gate overdrive, is because the current is limited by saturation velocity, which is independent of VGS minus VT. Okay? For the short channel MOSFET, basically, if you had looked at the sample of the old quiz, it was similar. Basically, you first had to calculate the electric field at which velocity saturation occurs due to this, and it's related to the mobility. Then you have to figure out the E sat times L. That's kind of the voltage, roughly the voltage at which saturation velocity is reached, and compare that with an ordinary pinch-off voltage, and basically use the equation that you're familiar with, hopefully, to calculate to estimate the actual drain saturation voltage. So it's slightly below 0.2 volts. So as long as you got around 0.2 volts, it's fine. And then the calculation for the saturation velocity limited current is relatively straightforward. You should have gotten some number around 1 milliamp. So as long as you draw a curve that sort of reaches saturation at slightly below 0.2 volts, or around 2.2 volts, and kind of a flat line, then you'll get full points. And Dibble, drain-induced barrier lowering, you had to mention that it is the reduction in the threshold voltage, or the reduction in the magnitude of the threshold voltage as you increase the drain to source voltage. Okay, so the drain depletion region is starting to affect the source potential barrier in the off state. So basically, since the threshold voltage decreases as you increase VDS, then you have a slope in the IDVD characteristic. IDVD characteristic, that's right. So you can either say that in words or you can just indicate it in the plot. Either way is fine. Okay. For short answer questions for modern CMOS, okay, why do we scale? You can have lower cost or higher transistor density, same thing. And then higher circuit performance. So either, if you just said higher circuit performance is fine. For digital circuits, it means shorter propagation delay. And for analog circuits, you have higher cutoff frequency. Another benefit is you improve the energy efficiency. You can lower the amount of power or energy you need to perform a given function. Okay, now why are the source drain regions designed to have shallow extensions and then deep contact regions? It's really to suppress short channel effect for the shallow region, and then you need deeper regions to just reduce parasitic series resistance. Okay? So 2 parts, that's why there are 2 points. Okay, why is it difficult to scale the gate length? Yes, Ross.
I thought the extensions were for the short channel.
That's right.
The shallowness was to avoid parasitic resistance.
Okay, the shallower your source drain junction, the less cross-sectional area you have for current to flow. So the shallow source drain extensions are actually more resistive, per unit length. So that's why you have the deep regions. So you have the deep regions farther away from the channel to reduce parasitic resistance.
RJ is the deeper region.
Well, for the short channel effect, RJ is the shallow region.
Isn't resistance like something over RJ?
Yes, so you want RJ to be larger, resistance to lower the resistance. Right. Yeah. Right. Okay. Part C. Why is it difficult to scale the gate length? Bottom line is because it's hard to suppress off-state leakage. So you have to provide some explanation. Why is it harder to suppress off-state leakage when you have a shorter channel device? You can say either like the short channel effect, VT being reduced as you scale down the channel length, or you can say drain-induced barrier lowering. It's just some explanation of why leakage increases as you scale the gate length down would be fine. Okay. One fine point that I probably didn't mention in class, basically gate control, you can suppress the VT roll-off, you can suppress drain-induced barrier lowering if you could scale the gate oxide thickness to continue to improve gate control over the channel. It's just that physically, the gate oxide cannot be scaled to be too thin, otherwise you get quantum mechanical tunneling and you don't have an insulating gate anymore. So part of the reason why it's difficult to scale transistors, the conventional transistors of very short channel lengths, is because of the inability for us to really scale down the physical thickness of the gate oxide. And also, if you want to increase the body doping to help suppress Dibble and short channel effects, actually you start to get N plus P plus junction formation in the drain, and that leads to Zener tunneling, right? Direct band-to-band tunneling. So the off-state leakage starts to go up. So it's counterproductive to dope the body too heavily for that reason. Okay, and then for the BJT, it's relatively simple. Hopefully you can see that this PNP structure. And since I mentioned we're operating at 1 milliamp, you should pick this curve that's saturating at 1 milliamp, roughly. And notice that there's 2 electron volt difference in Fermi level position for the emitter and collector. So that means there's 2 volt difference in bias between the collector and the emitter. So basically, that's how you pick this data point, or draw that dot there. And then on that curve, you can see the base current is 10 microamps, and the collector current is 1 milliamp. So you just take the ratio, and it's 100. Okay. And finally, if you increase the doping concentration by a factor of 2, well, the emitter ejection efficiency degrades because you'll have twice as many electrons injected into the emitter compared to holes injected into the base. So you don't like that. That's bad for efficiency of injection, because you would like to have most of the carriers injected from the emitter into the base. And then the transport factor, it doesn't change significantly. Yes, the depletion region widths in the base will decrease a little bit when you increase the doping. But that's why I sort of emphasize significantly. But if you thought that the base width actually increases so that the transport factor degrades, we'll accept that as well. But it's not as significant of an effect. Yeah, so a good question is, minority carrier lifetime, does that degrade if you dope the base more heavily? And the answer is usually no, because, so this is the difference. What determines the minority carrier lifetime is the density of trap states. So these are allowed energy levels near the mid-gap. So it's those kind of defects or impurities with energy levels near the middle of the band gap. Okay, so those are not the dopants. The dopants have energy levels close to the band edges. So that's a fundamental, point that in general, the dopants do not degrade minority carrier lifetime. But in practice, yes, sometimes more heavily doped regions have lower minority carrier lifetime because the process of doping causes more damage. So it's not inherent that the dopants cause that smaller minority carrier lifetime. It's just that the process results in more defects. Yeah. Other questions regarding this quiz? How'd you all do? Okay, all right, great. Okay, so for the rest of this semester, okay, so this week is the last week of regular lecture, but the material that I'm covering this week is basic, BJT, bipolar junction transistor material, so it will be covered on the final exam. And so to give you some practice, there's one final homework problem set that's extra credit. Okay, so it's optional. We'll release the solutions next Thursday. So it's optional only for extra credit, but it's just basically so you can have some practice working on some problems that will be similar to those on the final exam. Okay? No, the homework, so there will be another homework assignment put out this week that will be due next Thursday. So next week, I guess we'll post the schedule. Is that right, Peng? So basically, next week we'll have like 20-minute time slots for presentations by the graduate students on their project. So the presentation should only be about 10 minutes, okay? I was allocating 20 minutes just to allow plenty of time for questions and people, plugging in. And last semester, people had problems with the computers, so that delayed things. So undergrads are welcome to sit in and watch any project presentation they want. We'll post the schedule in advance so you can come here and support people you want to support or not. I guess you can ask questions too, but yeah. So next week basically is just no lecture, just project presentations during the regular class time. We will have regular office hours and discussion sections because the discussion sections will cover the material that we introduced in class this week. Okay? Now, Peng and I believe that you are all keeping up with the material in this class, so you do not need a final review session. Is that, I just want to confirm, is that true? I mean, no? Okay, so how many people think that would be good to have a final exam review session? Wow. Okay. When is the final exam? I don't even remember when. It's on a Tuesday. Okay, so which day would be the best to hold a review session? What day and time, actually? Tomorrow? Oh, not tomorrow. Oh, during RRR week. Okay. All right. Because I don't want to conflict with any other classes you have.
Did you do either Tuesday or Thursday?
Yeah, so maybe immediately after class on a Tuesday or Thursday, I can find out if this, I basically have to reserve a classroom. So how about like right after the normal class session on next Tuesday or Thursday? Okay. All right. That sounds good. Wait a minute. So that means that's during RRR week? Okay, but there's like a social hour, right? I was thinking. So maybe after next Thursday. So after class next Thursday. Is that reasonable? Okay. Sounds good. Thanks. Okay. So today, so the rest of this week, we're just going to finish up the bipolar junction transistor. Today, actually, I don't think I'll finish all of the notes, but I will definitely finish all of the lecture notes by the end of next lecture. Yes, Peng? Oh, yeah, so so there's some issues with the campus power supply, so that's why we don't have network access. But anyway, we've announced on the class website that projects, so some of you have already finished your project, so you can hand them in anytime in class, like today or this Thursday or next Tuesday or next Thursday. And if you turn it in after class next Thursday, just turn it into my assistant, Meg. She's the one who handles the social hours, but her office is right next to mine in Corey Hall. So as long as you turn it in physically by 5 o'clock next Thursday, it'll be considered on time. Okay? Are there is anybody struggling to get the project done? I mean, any logistical issues there? No? Okay, great. Well, since some people have already finished, I think that's a good sign that it's doable, right? All right, so today we're going to talk about 9 ideal effects in modern BJT structures. All right, so last time we talked about the base width modulation effect. So if you look at a typical output characteristic, so that's current versus the output voltage for a common emitter configuration. So this is, again, to remind you, we're plotting the BJT current as a function of the output voltage. But as we increase the output voltage, we're increasing the reverse bias on the collector junction. So eventually, last time we were talking about pretty low voltages, few volts, less than 10 or 20 volts. But if you actually try to apply a large voltage, like close to 100 volts across the base, the collector emitter terminals, you'll see that eventually you'll conduct a lot of current in your BJT. Okay, so there are 2 possible reasons for this non-ideal current flowing directly between the collector and the emitter at high gate collector to emitter voltages. So let's talk about both of them here. The first one is punch through. That's basically base width modulation to the extreme. In other words, you modulate the base width down to 0. Okay, so basically the depletion region in the collector punches through to merge with the depletion region in the emitter junction. So that's punch through. The other possible way to conduct a lot of current, even if there's not much forward bias on your emitter junction, is avalanche breakdown of the collector base junction. So we'll talk about those 2. So usually, do you remember the avalanche breakdown for a PN junction? It was pretty abrupt, right, basically. So these curves here, this abrupt increase right here, this would be due to So anytime the current is actually increasing really rather abruptly, then that's an avalanche, a characteristic of an avalanche mechanism taking place. And this more gradual increase in current with voltage is then more likely due to punch through. Okay, so let's cover punch through first. So up on the upper left, we show the depletion regions of the collector base junction and the emitter base junction merging so that the base width, the quasi-neutral base width is 0. Okay, so this is the depletion region of one junction and depletion region for another junction there. Okay, so that phenomenon causes current between the emitter and collector to increase. This is a little bit like Dibble in the MOSFET in the off state. Okay, so this is, except now we're talking about PNP kind of a structure instead of an NPN. But basically, once the base is base width, quasi-neutral base width goes to 0, you actually don't have any flat band bending portion in the, you don't have any flat energy band diagram in the base region anymore, right? Because there's no quasi-neutral region. So basically, you have band bending because there's charge, non-zero charge in the base throughout the base region. And as you increase the output voltage, you're increasing the reverse bias on the collector junction. So remember, if you're increasing the reverse bias on a PN junction, you're increasing the potential barrier, right, to carrier diffusion. So basically, you can see from this energy band diagram, right, there's a huge voltage drop across this PN junction, and that only increases. So this arrow, right? So going from the solid line to the dashed line, that's basically representing an increase in the reverse bias on the collector junction. In other words, an increase in the output voltage. So the key thing to note is right here near the emitter junction, that potential barrier to diffusion of carriers into the base, and oppositely, from the base into the emitter, this potential barrier height to diffusion starts to become affected as you increase the reverse bias on the collector junction. Okay, so if you reduce the potential barrier to carrier diffusion, you increase roughly how do you increase the current, the diffusion current across the emitter junction? Exponentially, right? It increases super linearly, right? So remember, the number of holes with enough kinetic energy to diffuse into the base here will increase exponentially as you reduce the height of that potential barrier. So that's why the current actually can increase pretty significantly as you increase the reverse bias or the output voltage of the BJT. Okay? Yeah, so let me just illustrate. So the normal case is that you would have something like this, right, for normal PNP diode, BJT. Yes, that's normal. You have some, almost some flat region here. But with punch through, you don't have that anymore. Okay? So is this potential barrier height is reduced compared to the normal. This is basically what happens when you increase VCE. All right, any questions just qualitatively about the punch-through effect? You only need to understand it qualitatively. Well, maybe how do we mitigate this effect? If we do want to operate the BJT with really large output voltage, how would you design this BJT differently to be able to operate with high output voltage, like for a power transistor? That's right. So you can increase the doping in the base, or increase the width of the base. Yeah, and the trade-off is degraded gain. That's right. So there's always a trade-off in a BJT design. Okay, the other way that this current can suddenly increase with increasing output voltage is avalanche. So notice in this energy band diagram here, there is a flat, base region, and so that means that you're not punching through the base. Okay, so one interesting thing about a BJT, basically having these two junctions so close together, is that carriers can easily diffuse. Minority carriers can easily diffuse across the quasi-neutral base region and affect one junction. I mean, if the carriers generated at one junction or introduced from one junction can actually easily get collected by the other junction and affect what's going on there. So let's go through this a little bit slowly. So ordinarily, when avalanche occurs in a p-n junction, you have to have a relatively high electric field in the p-n junction depletion region. Right? So that's what's shown here. Right? So in this region, you have a relatively high E field. Right? So relatively steep energy band diagram because within, let's say, a typical mean free path, the carriers can gain enough kinetic energy so that when they scatter, they can lose enough energy to generate an electron hole pair. Right? So this energy that this electron loses when it's scattered, this kinetic energy is greater than the band gap energy. So it can lose the energy to a covalent electron or valence electron and have that valence electron move up to the conduction band. Okay. All right. So basically, for avalanche to occur, you have high electric field in the base collector junction, and if you have any hole, okay, if you have any hole that's flowing, being collected by the collector junction, that hole will traverse the depletion region, and that hole, okay, so rather than the hole causing electron hole pair generation, the hole, when it's being collected by the collector, can lose enough kinetic energy to generate, to cause an electron to move up from the valence band into the conduction band. Okay. Now that electron can go on and generate electron hole pairs, and the generated hole can also generate electron hole pairs. Okay. But let's just say for a simple example, that electron that is generated will now drift and can actually flow into the emitter. Okay, let's summarize that. So you turn on the BJT just a little bit. So holes diffuse into the quasi-neutral base. They're collected by the collector, but when they're in that high field region in the collector junction, they generate an electron hole pair. Now the hole gets collected, the generated hole gets collected with the original hole, but the generated electron comes back and eventually can diffuse into the emitter. Okay. Now when the electron diffuses into the emitter, remember there's a law, well, it's like a rule of the junction. For every electron that diffuses from the base into the emitter, there are going to be many more holes that diffuse from the emitter into the base. Right? The ratio of carrier diffusion across the junction is sort of determined by the ideal diode equation. Okay, so step 5 is basically just saying, okay, if you have like one electron diffusing into the emitter, then you must have like 100 times more holes diffusing into the base, assuming that, let's say, maybe the emitter is doped 100 times more heavily than the base. Okay, it might not be 100 times, but it's on that order. Okay, so realistically, what's going on? If an electron is generated in the base collector junction depletion region, because of the electric field, it'll just go to the base, right? But then the base will be sort of negatively charged. Okay, so this p-n junction, just imagine the base will get charged up by electrons, and that eventually will reduce the forward bias on the base emitter junction. Right? So eventually, what happens is, I mean, the electrons have to diffuse. This generated electron has to diffuse into the emitter. Otherwise, it'll just stay there in the base, and it'll actually forward bias the base, right, more. So that lowers the potential barrier and causes the electron to flow across. So basically, for every hole, hole that you originally inject into the base and that is collected in the collector, you actually can end up with multiple holes. You can cause additional multiple holes to diffuse and be collected by the collector. I mean, there's an internal gain or internal amplification occurring here. Yeah, yes, Paroma. Okay, so the question is, can you have a combination of avalanche and punch-through? So punch-through occurs, oh, I see. Okay, so punch-through occurs if you like get rid of the quasi-neutral region in the base. So that it is possible. So like in some of these curves here, probably you're ending up with both punch-through and avalanche occurring at high. So at high current levels, and yeah, right, at high current levels, you could have both occurring. Okay. So the key is that you have more. Actually, it's more than a factor of beta sort of amplification going on here. And so for that reason, it actually turns out that the breakdown voltage for the collector emitter structure across so the largest voltage you can sustain with before seeing lots of current flow across the collector emitter junction is actually less than the collector junction breakdown voltage, right? So it's easier. Let's put it this way: it's easier to break down or have avalanche occur for a PNP or for a BJT compared to just a PN junction because of this internal amplification process. Okay, and that's only possible because the base is so narrow that carriers that are collected, minority carriers that are collected in, or actually majority carriers, can actually start to influence what's going on in the emitter. Okay, so this factor of M actually is just empirical. M is anywhere between 2 and 6, as indicated on this slide. But it really depends on the geometry of the junction again, like how sharp and rounded the corners of the junction are and so on. Okay? So this is just an empirically determined factor, M. Okay, so the question is, would you ever want to cause avalanche to occur? Yeah, so Zener diodes, okay, so that's a good question, because Zener diodes, we do design them to operate. We do design Zener diodes to provide very steep turn-on in current if we want to limit like the voltage across a circuit. That's a good question. So, okay, so the question is, do we ever want, well, okay, we generally don't want punch-through ever to occur, okay, because that's not nice and sharp. Avalanche, again, like maybe like an avalanche photo transistor, like we might want that to happen. But I think for a circuit, if you want something like this, it's probably easier to make a diode, simpler, cheaper, yeah. But yeah, for a photosensitive BJT or photosensitive transistor, you might want to operate it in the avalanche regime, yeah. Mm-hmm.
But in this case, I think.
So the question is, yeah, this is a pretty high breakdown voltage, 90 volts. Yeah, so it depends on how the transistor is designed. So for an integrated circuit, yeah, we would never have, the transistors have very short regions, and so they would never be able to withstand this kind of voltage. So these are more typical current versus voltage characteristics for discrete, like individual transistors that you could use in your lab, and so on. Yeah, yeah, you're right. This is not typical for an integrated circuit. Okay, so the question is, can you design an individual transistor that can withstand high voltage? Yes, sure. Yes, you just have to make the base width wide enough and the doping levels, not reasonable to withstand that. In fact, there are whole textbooks that are written on how to design BJTs for different applications. If it's for switching applications or amplification applications. So for high voltage switching, you would design actually the base and the doping and the collector, especially the collector doping and the length of the collector region. That is quite different for the different applications. Yeah. So most of this voltage can be dropped across the collector region, the collector junction. Okay, so that's it. So that's one non-ideal behavior. Other non-ideal effects, there's two classes. Similarly to a PN junction diode, non-idealities show up at very low current levels and also at very high current levels. Okay, so it's very similar to a PN junction. It's the same. This generation recombination current component is usually small, and so we don't care about it unless you're operating a PN junction at very low voltage and therefore a very low current level. Okay, so technically the injection efficiency of the emitter junction is equal to the current due to carriers injected into the base divided by the total current that's flowing across the emitter junction. And the total current can have this non-ideal recombination generation component. Okay? So this only becomes significant if these other components are relatively small, and that happens at relatively low forward bias on the emitter junction. Okay, so what qualitatively all you have to see, hopefully, is that, well, that just degrades the emitter injection efficiency and therefore degrades the current gain. Okay, so in other words, you can't operate, well, we'll see in the plot later. If you operate a BJT at very low current levels, then the current gain goes down. Okay? Now, on the other extreme, if you operate a BJT transistor at very high current levels, in other words, at high forward bias on the emitter junction, you also see a degradation in current gain. But that degradation, and I apologize, there's a mistake here. That degradation is due to high-level injection. So if you remember from PN junction diode, if you apply a large forward bias on a PN junction diode, you end up disturbing the majority carrier concentrations in the quasi-neutral regions. And the majority carrier diffusion currents start to become significant, and they counteract the minority carrier diffusion currents. So the current, as you increase the forward bias on a PN junction, you can't increase the current as quickly anymore. And that's manifested right here with this extra factor of 2 in the exponential term there. Okay? So if that happens, okay, so remember, beta is defined to be the ratio of the collector current over the base current, and this is in the active mode of operation only. Okay, so what I showed previously, what this does is it actually degrades IB. Okay, I mean it basically makes IB larger than ideal. Sorry, so this effect at low VEB makes IB larger than ideal. Okay, because you have this extra recombination generation current, and for that reason you degrade the current gain. Here we degrade current gain because IC is going to be lower, or increasing slower than ideal, more slowly than ideal. Okay, so let's just plot this. So if you have log of IC versus VEB, ideally it should be a straight line, a log on a log plot, but then it sort of bends off at high values of VEB, at high current levels. Okay? So this, again, is due to significant majority carrier diffusion current at high level with high level injection. Okay, for a PN junction diode, remember at high current levels, another reason we see it decreasing, or this current not increasing ideally, is because of series resistance. So remember in a PN junction, in a BJT, let's draw a BJT structure. We have contacts for interconnects up here, emitter base collector contacts. Series resistance. So current actually flows through the emitter and then the base and then into the collector, and it has to flow out somewhere, along here to flow out to the collector contact. So as the current flows, there are resistances, right? These are doped semiconductor regions. They don't have really zero resistivity. They have some non-zero resistivity, so that will result in some resistance in this current path. Of course, the base is rather short, and the emitter is rather short and very heavily doped. So really, it's a lot of parasitic resistance from the collector that can cause. So if you have high amount of current flowing here, you can end up with a significant voltage drop across the resistive collector region. Okay, so then that effectively reduces the real voltage that you're applying to the transistor, and so that the current doesn't increase as quickly as you increase the voltage applied to your metal contacts. Okay, another thing that's interesting in a bipolar junction transistor is that, well, here's your base emitter junction, right? It's here. So technically, current can flow anywhere between the P plus and N regions, and between the N and P regions, like along the sides of the junctions as well as the bottom. Okay, so what happens is that as, let's say, holes are injected into the base region, they can spread out. Okay, so you can actually have holes basically flowing kind of in a 2D kind of a pathway like this, right? So there's spreading occurring. And actually, the electric fields generally are higher at the corners. So it turns out that there's more current that tries to flow near the corners. Okay, so this is called current crowding because the electric field is not really uniform. So you end up with more current density sort of in the corners. And with higher current density, you get more Joule heating, right? So power dissipation. Anyway, so you get more heating here, and actually then you end up with what happens to the resistance of a semiconductor generally when you heat it up. It increases, right? Assuming it's not really super heavily doped, right? So the collector is not super heavily doped. So if you heat it up, resistance will go up. So you end up with some non-uniform heating, and then resistance goes up. So this is current crowding actually falls under series resistance. It's kind of like one type of it's a phenomenon that leads to significant series resistance at high current levels. Okay. Why does Joule heating? Oh, okay. So when you flow current through a semiconductor, okay. So that's yeah. So remember, okay. Well, no, it's like this. Let's see. So remember, like early on in the semester, we talked about visualizing carrier flow. Okay, so if you have an electric field, let's say pointing in this direction, and you have electrons, now how do they flow? They actually flow and they collide, right? They get scattered, they lose their kinetic energy, they get accelerated by electric field. So carriers get scattered as they flow, so holes going in the opposite direction. So they scatter with the lattice or with impurities, and they lose their kinetic energy to the lattice. So basically, as carriers drift in a semiconductor, they heat up the semiconductor, right? They're losing their kinetic energy to the lattice, and that heats it up. So if you have a high current density, this heating effect becomes significant, and that's actually, yeah, bad for the resistance. And so it's harder and harder to increase the transistor current as you go to higher and higher voltage. Okay? Yeah. So that's qualitatively what that is all about. So bottom line is, if you plot on a log scale both the collector current, so this is IC and IB, sorry. So on a log scale, each of these should be a straight line, okay? And what is the slope of that line? Just if you remember. How many millivolts per decade? 60 millivolts per decade, yes. So both IB and IC should be 60 millivolts per decade. But at low base emitter voltages, the recombination current component becomes significant. So remember, for a PN junction diode, this is the ideal diode current. It would just keep going down. But now you have this recombination current component that's significant when the normal diffusion current is low. Now, when you go to higher voltages, the diffusion current component becomes dominant. So you don't see that impact of the recombination current. Okay, and at high levels of current, then the collector current doesn't increase with the same slope. So in these regions here, you have beta, which is the ratio of IC over IB. In other words, on a log plot is the distance, the separation, the vertical separation between these two curves. So you can see on a typical plot on the right, if you plot the DC common emitter current gain, beta, it actually drops off at low values of current, and it also drops off at high values of current. Okay, so just qualitatively, you should be aware, like if you're a circuit designer, that okay, the beta is usually spec'd within a current, a range of operating currents, and if you go out of that range, then the beta will drop off. Okay. Okay, so the equations that we've developed, like last time, were pretty simple because we assumed uniformly doped source and drain, emitter, base, and collector junctions. Okay. In reality, these regions are not uniformly doped, and I'll sketch that on the next slide. But let's just introduce the concept of a Gummel number. So on this slide, the Gummel number is essentially defined to be the total dopant concentration, well, per unit area in the base. And then you divide out, you normalize it or sort of weight it by the diffusion constant. So this is a definition, well, this is for a uniformly doped base. The Gummel number is defined to be dopant concentrations times the width of the base. So that's the total number of dopants per unit area in the base. And then you divide it by the diffusivity of minority carriers in the base. Okay? So if we use this definition of Gummel number and look at the ideal equation for the collector current, you can see that the collector current depends on the Gummel number. Okay? So qualitatively, the larger the Gummel number in the base, the worse your collector current for a given gate voltage, for a given base to emitter voltage. In other words, you don't really want to you don't want to have a lot of dopants in the base if you want to have high current gain. So if we actually look at the equation for emitter efficiency, on which the current gain depends quite heavily, you can see you can just write it as a ratio of Gummel numbers, the base Gummel number and the emitter Gummel number. Okay? So the emitter Gummel number is defined similarly as the base Gummel number. So it's defined to, well, for a uniformly doped emitter, it's NE times the width of the emitter, actually the quasi-neutral emitter, divided by the diffusivity of minority carriers in the emitter. Okay? So that's just, so it's helpful to remember that the current gain is roughly equal to the ratio of the emitter to the base Gummel number. So what this means is that you like to have generally more dopants in the emitter than in the base to have high current gain. All right? Okay, so the reason why people care about Gummel numbers is because in reality, when we make a BJT, let's look at the dopant concentration versus depth. Okay, so let's assume we start with a uniformly doped silicon wafer, and it's doped at, this is ideal, it's doped at some concentration level corresponding to your collector region dopant concentration. Okay, then during the fabrication process, we can introduce some dopants, usually by implanting them and diffusing them, heating the wafer to a very high temperature and allowing the dopants to diffuse. But generally, that results in a profile that looks kind of like this. Okay, so this might be the base doping profile as a function of depth. Okay, so it's not uniform. And then finally, we would introduce maybe even more heavily doped emitter that's rather shallow. And it's also a function of depth, but it's not, certainly not a uniform dopant concentration within the emitter region. So let's sketch this. Okay, so this, where the dopant concentrations equal, those are the metallurgical junctions. Right? So this is where the collector is. And then you have the base region here. And then we have the shallow emitter region there. But you see the key here is that the dopant concentration in reality is not going to be like a nice box-shaped profile. It's going to actually be dependent on the depth. Okay? So the concept of the Gummel number is useful because what it says is that, okay, all we care about is the integrated dose. Right? So we integrate the dopant concentration as a function of depth. See, so for a uniformly doped BJT, this would just be NB times W, right? If you take the integrated dopant concentration in the base, that would be just NBW. But in the more general case, you just integrate the profile like this, and that would, and divided by the average, the minority carrier diffusion coefficient, and that would give you the Gummel number for this BJT. And same thing for the emitter Gummel number. You just take the integrated dose of the dopants in the emitter and divide by the average minority carrier diffusion coefficient, and you can get the emitter Gummel number. Then you take the ratio, and that will give you a good estimate of the current gain of that emitter, of that BJT. Okay? Even though it's not an ideal BJT with uniform doping concentrations. Okay? So that's the benefit of the Gummel number, the concept of a Gummel number. Okay. Okay, so let's end on this. So this is the modern BJT structure. Let's see. So hopefully you recognize that the BJT is actually right here, the intrinsic device. Oops, is actually like, I even overdrew it. It's like right here. Right, so the beat, and this is this is an NPN device. But basically, what I've just boxed out there, that is the, that's the BJT. Everything else is sort of extrinsic, the extrinsic portion of the structure to allow you to make contacts to the emitter, to the base, and the collector regions. Okay, so let's highlight some of these features. Okay, so hopefully, I've already mentioned this a couple of times, but the collector is usually lightly doped, right, for various reasons. We don't want to have base width modulation to be significant. So the collector is more lightly doped than the base, which has to be more lightly doped than the emitter for good injection efficiency. So in order to get current out through the surface, there's a metal contact here, we actually want to form heavily doped N-type regions to minimize the resistance of the current path for the current to flow into and out of the collector. Okay, so that's what the sub-collector is for, and then you have this N+ doping. Now for the base, you also, it's not super heavily doped, it's moderately heavily doped. You would like to have low resistance contact regions. So you generally, in advanced structures, they do use heavily doped P-type silicon, and the dopants in the P-type silicon actually naturally will diffuse into the silicon here. So you have self-aligned, heavily doped P-type contacts to the intrinsic base region. And then finally, you can deposit a very heavily doped N-type silicon layer and diffuse. So usually what we do is deposit a very heavily doped polysilicon layer over the base and have the N-type polysilicon touch the base region like this. And then we heat it up, and the N-type dopants diffuse from the N-type polysilicon and sort of, so this part here is diffused into the P-type base region to form the single crystalline emitter portion. Okay, so here are the features, the base. So this way, okay, so actually, why would we want to diffuse, if people who took 143, why would you want to diffuse dopants to form the base emitter junction versus implanting an anneal? less damage, that's right. So you don't have that non-ideal recombination generation current. So diffusion is not damaging to the crystal. That's very good. Also, you might be able to better control the width of the quasi-neutral base region. I mean, diffusion can be a slow process if you anneal at moderate temperature. So this quasi-neutral or this base width here can be more precisely controlled if you diffuse it. Okay. Oh, and then just like for MOSFETs, we have deep trenches etched into the silicon and filled with silicon dioxide. So these are to electrically isolate one transistor from the other. So everywhere where you see this light blue, this is insulating, non-electrically conductive silicon dioxide to isolate this structure. Okay. Let's see if there's anything else. Okay, so let me just put in some numbers here. So it's typically less than 0.1 micron. Emitter might be on the order of less than 0.5 micron thick. And these self-aligned contacts are for reduced base resistance. So let's call it R sub B. A lightly doped collector for large early voltage, so to minimize the base width modulation effect. Heavily doped epitaxial subcollector is for reduced collector resistance, and that's pretty much it. Yes, question. Which shape on top? For the emitter. Oh, okay. So the question is, why do we have this? Okay. All right. We'll end here. Okay. So the reason. Okay. So we have this silicon. Okay. How do we? Okay. So the base contacts here are formed first, right? So these. Let me change colors. So these base contacts, these p-type, P+ polysilicon regions, film is deposited first, and then encapsulated with this silicon dioxide to electrically isolate it, from this emitter contact. But the key is that the P+ polysilicon is deposited and patterned first to form these contacts to the p-type base. Then we deposit the oxide, and we have to etch holes in the oxide layer. And then, so just naturally, because you're etching holes in this stack, this polysilicon thin film that's deposited last is deposited conformally, so it comes down like that. That's the only reason. It's just because you build it up, you deposit and pattern one layer at a time, and you end up with surface topography this way. Oh, yeah, the question is, can we put a collector contact on the other side to make it symmetric? Yes, that's true. You can do that, but it takes up more layout area, more space, so it's not as compact. So it turns out that you only need, because this is pretty heavily doped, so you can have a low enough resistance. Yeah, so it's really the layout area savings. For the base, it turns out, okay, so next time we'll talk about the AC or high frequency performance. The base resistance actually is more important to minimize compared to the collector resistance. Because that determines VBE, right, the real voltage that you apply across the base emitter junction. So people take more pains to form very, very low resistance contacts very close to the intrinsic portion of the transistor for the base contact. Yeah. Okay. Great. So we'll finish, don't worry, we'll finish next time. So today we have a social hour with Professor Paxson